For centuries, we have looked to the skies with a mixture of awe and fear. We've charted the stars, named the clouds, and built entire civilizations at the mercy of the elements. Our greatest tool has been the weather forecast, a complex, data-driven attempt to glimpse into the immediate future. But it's always been a glimpse through a foggy window. We see shapes, we see possibilities, but the fine details remain hidden, often until it's too late. Now, imagine a technology that doesn't just look through the window, but opens it, stepping directly into the intricate dance of atmospheric particles. Quantum computing isn't just an upgrade to our current methods. It's a completely different language. It's a language that speaks to nature on its own terms, the strange, probabilistic, and interconnected language of quantum mechanics. By harnessing this power, we are on the verge of creating weather and climate models so precise they can anticipate extreme events not just days, but weeks in advance. This isn't about knowing whether to bring an umbrella tomorrow. This is about knowing when to evacuate a city next month. It's about building a shield against the fury of nature, and in doing so, rewriting the future of human survival on this planet. To understand why this quantum leap is so vital, we must first confront a harsh reality. Every year, the story is the same, written in headlines of loss and devastation. Severe weather is not a rare occurrence. It's a relentless, recurring disaster. In the United States alone, the cost of weather-related catastrophes routinely exceeds $100 billion annually. But the true cost can't be measured in dollars. It's measured in lost lives, shattered communities, and futures washed away by floodwaters or scattered by wind. Hurricane Katrina, Superstorm Sandy, the devastating tornado outbreaks in the Midwest, these are not just historical events. They are scars on our collective memory, stark reminders of our vulnerability. The core of the problem lies in the warning gap. Our current supercomputers, for all their incredible power, are fighting a losing battle against chaos. They provide warnings, yes, but often these warnings come with a wide cone of uncertainty and a ticking clock that offers mere days, sometimes only hours or minutes, to prepare. Think of a coastal community facing an approaching hurricane. A 5-day forecast might show a massive cone of uncertainty spanning hundreds of miles of coastline. Do you evacuate millions of people, grinding the economy to a halt, based on a probability? Or do you wait for more certainty, risking that by the time you have it, the highways are clogged and it's too late to escape? This is the impossible choice that emergency managers and ordinary citizens face time and time again. Our current models fail to provide the timely, specific intelligence needed to act decisively. They can't fully capture the intricate feedback loops and microscopic triggers that cause a storm to suddenly intensify or swerve unexpectedly, leaving communities tragically unprepared when nature's full force strikes. So why is weather so notoriously difficult to predict? The answer lies in a concept you've probably heard of, the butterfly effect. It's the cornerstone of chaos theory, the idea that a single, infinitesimally small event, like the flap of a butterfly's wings, can cascade through a system and produce enormous, unpredictable consequences weeks later on the other side of the world. The atmosphere is the ultimate chaotic system. It's a turbulent ocean of air, where every molecule of water vapor, every particle of dust, and every ray of solar energy is part of an unimaginably complex equation. To try and solve this equation, classical supercomputers use a technique called numerical weather prediction. Imagine trying to build a perfect digital replica of the Earth's atmosphere. The way we do it now is by laying a giant three-dimensional grid over the planet. Each box in this grid might be a few kilometers wide. The computer then calculates the temperature, pressure, humidity, and wind within each box and uses the laws of physics to predict how those values will change and affect the neighboring boxes in the next few minutes. It then repeats this process, step by step, minute by minute, to build a forecast. But here's the fatal flaw. The real atmosphere doesn't operate in neat little boxes. The crucial interactions, the formation of a single water droplet that releases latent heat. The tiny eddy of wind swirling around a skyscraper happen at a scale far smaller than our grid can see. We have to approximate to average out the chaos within each box. This is like trying to describe a Monet painting by listing the average color of each square inch. You might get the general idea, but you lose all the texture, the brushstrokes, the genius of the piece. To make the grid finer would require an exponential increase in computing power, a mountain so high that even our best classical supercomputers can't climb it. We are trying to capture a fluid, interconnected reality with a rigid, blocky tool. It's an impossible task, and it's why even the best forecasts eventually break down into statistical noise. This is where quantum computers change the game entirely. Instead of trying to force the atmosphere into a grid of simplified boxes, a quantum computer embraces its inherent complexity. It bypasses the classical limitations, because at a fundamental level, the universe is quantum. The interactions of molecules, the behavior of energy, the very fabric of our atmosphere, all follows the strange rules of quantum mechanics. So, what if we build a computer that operates on those same rules? A classical computer bit is like a light switch. It's either on or off, a 1 or a 0. But a quantum bit, or qubit, is like a dimmer switch. Thanks to a principle called superposition, it can be a 1, a 0, or both at the same time, holding a spectrum of possibilities simultaneously. Furthermore, through entanglement, what Einstein called spooky action at a distance, qubits can be linked. The state of one instantly influences the state of another, no matter how far apart they are. What does this mean for weather? It means a quantum computer can model not just one possible future for a pocket of air, but a vast number of potential futures all at once. It can directly simulate the probabilistic nature of molecular interactions, the very foundation of atmospheric physics. It doesn't need to approximate the turbulence inside a thunderhead. It can model the quantum dance of the water molecules themselves. It can capture the nonlinear feedback loops where ocean temperature subtly affects wind shear, which in turn affects cloud formation, which then alters the amount of sunlight hitting the ocean, not as a series of disconnected steps, but as a single, holistic, interconnected system. It's the difference between reading a book one word at a time and absorbing the entire story in a single intuitive flash. This isn't just a faster way of doing the old calculations. It's a new way of thinking, a new way of computing that aligns perfectly with the chaotic, quantum nature of the world it's trying to predict. This isn't just theory anymore. Around the world, in specialized research labs and forward-thinking meteorological centers, early-stage quantum systems are being deployed, and the results are nothing short of staggering. They are validating what was once only a tantalizing promise. Let's put this in concrete terms. Take hurricane track prediction. For decades, a major goal has been to shrink the cone of uncertainty. With quantum-powered models, we're seeing early results that are up to 10 times more precise than the best classical models. Imagine what that means. Instead of telling the entire Florida peninsula to brace for impact, you can pinpoint the 20-mile stretch of coastline that will bear the brunt of the storm 2 weeks in advance. This transforms evacuation from a logistical nightmare into a targeted, life-saving operation. Or consider tornadoes, the most violent and unpredictable storms on Earth. The average warning time for a tornado is about 13 minutes, barely enough time to get your family to the basement. Quantum simulations are beginning to identify the complex, small-scale atmospheric conditions that spawn supercell thunderstorms with a lead time not of minutes, but of hours. An alert that says, the conditions over your county are becoming highly favorable for tornadic activity within the next 2 hours, is a paradigm shift in public safety. And it's not just about intensity, but longevity. A traditional 10-day forecast is notoriously unreliable by the end. The quantum models being tested are showing reliable, high-confidence forecasts that extend for weeks. This allows not just for immediate safety, but for strategic preparedness. It gives utility companies time to pre-position line crews, relief agencies time to stage supplies, and governments time to mobilize resources long before the first drop of rain falls. We are witnessing the birth of proactive, rather than reactive, disaster management. This revolution isn't happening in a vacuum. It's a global race to harness this new power, and pioneers in Europe, Japan, and the United States are already demonstrating its transformative impact across vastly different climates. In Europe, where deadly heat waves are becoming more frequent and intense, a quantum-enhanced model recently predicted the formation and persistence of a heat dome over the Iberian Peninsula, a full 3 weeks in advance. This wasn't just a general "it's going to be hot" forecast. It detailed which specific cities would experience the most dangerous temperature spikes and for how long. Armed with this knowledge, authorities were able to issue public health warnings, open citywide cooling centers, and adjust power grid operations to handle the surge in demand for air conditioning, saving countless lives, particularly among the elderly and vulnerable. In Japan, a nation perpetually in the path of powerful typhoons, a joint research initiative used a quantum-inspired algorithm to reanalyze the path of an approaching storm. Classical models showed it heading for a glancing blow. The quantum analysis, however, picked up on subtle ocean temperature variations and high-altitude steering currents that the old models miss. It predicted a sharp, last-minute turn directly toward a densely populated coastal region. While the warning was unconventional, authorities trusted the new data. A targeted evacuation was ordered for a handful of towns. The storm made the exact turn the quantum model predicted, and a potential catastrophe was averted. And in the heart of America's Tornado Alley, researchers are using quantum simulations to understand the why behind tornado formation. By modeling the intricate dance of wind shear, updraft, and moisture at a near-molecular level, they are developing new warning systems. In one pilot program, the system gave a 3-hour window for a developing supercell, allowing a rural school district to cancel after-school activities and send every child home safely, long before the sky turned a menacing shade of green. These aren't just data points. They are stories of lives saved, proof that this technology works in the real world. The power to see the future of our atmosphere extends far beyond saving lives in a disaster. It's a tool that is set to redefine efficiency, profitability, and sustainability across nearly every major industry. The ripple effects are creating a world that is not only safer, but smarter and more productive. Consider agriculture, the foundation of our civilization. For a farmer, the weather is their most unpredictable business partner. But with quantum forecasting, that partnership changes. Imagine a vineyard owner in California receiving a precise, long-range forecast predicting a period of unseasonable frost 3 weeks from now. They have time to invest in and deploy protective measures, saving an entire year's harvest. A farmer in the Corn Belt can know the optimal 48-hour window for planting, a window that perfectly balances soil moisture and incoming rainfall to maximize crop yield. This leads to more food, greater stability in our supply chains, and better use of precious resources like water and fertilizer. Look to the energy sector, which is in the midst of a massive transition to renewables. The biggest challenge for wind and solar is intermittency. The wind doesn't always blow, and the sun doesn't always shine. Quantum weather models can predict lulls in wind speed or the passage of a dense cloud bank over a solar farm with uncanny accuracy, days in advance. This allows grid operators to seamlessly balance the power supply, bringing conventional power plants online exactly when needed and storing excess energy with maximum efficiency. The result is a more stable, reliable, and cost-effective green energy grid. And in aviation, safety and efficiency are paramount. Airlines currently rely on short-term turbulence reports to adjust flight paths. A quantum system can predict the formation of clear air turbulence, one of the most dangerous and invisible threats to aircraft, weeks ahead of time along major flight corridors. This allows for the creation of flight plans that are not only safer and more comfortable for passengers, but are also more fuel efficient, saving millions of dollars and reducing carbon emissions. From the food on our tables to the electricity in our homes and the planes in our skies, quantum weather prediction is becoming the unseen engine of a new industrial revolution. Perhaps the most profound application of this technology lies in its ability to zoom out, to shift our focus from the weather of next week to the climate of the next century. If weather is like a single day's mood, climate is the underlying personality of our planet. Understanding that personality and how we are changing it is the greatest challenge of our time. Classical climate models, while heroic in their effort, suffer from the same limitations as weather models. They are forced to make broad assumptions about incredibly complex, slow-moving systems. The intricate dance between the deep ocean and the atmosphere, the precise physics of melting ice sheets, the subtle feedback loops of the global carbon cycle, these are phenomena that unfold over decades and continents. Simulating them accurately has been beyond our reach. Quantum computers offer a path forward. They are uniquely suited to modeling these vast, interconnected systems with a level of fidelity we've never seen before. Scientists can now run simulations that capture the delicate exchange of heat between the ocean's surface and its deepest trenches, a key driver of long-term climate patterns. They can model the microphysics of ice crystal formation and fracture, giving us a far clearer picture of how quickly our polar caps will melt and sea levels will rise. This isn't just about confirming that the planet is warming. We already know that. This is about moving from a blurry global average to a high-resolution regional map of our future. A quantum climate model won't just tell us the average global temperature will rise by 2 degrees. It will tell a specific coastal city in Bangladesh how far the sea will encroach upon its shores by 2050. It will tell farmers in the American heartland how the pattern of droughts will shift over the next 30 years. It gives us the specific, actionable intelligence we need to build defenses, adapt our economies, and protect our future. It's a tool that can help us move from arguing about the problem to collaborating on the solutions. As powerful as these current breakthroughs are, we are only scratching the surface. The quantum systems of today are like the Wright brothers' first flyer, a revolutionary proof of concept. The systems emerging tomorrow will be like supersonic jets, integrating not just the atmosphere, but entire Earth dynamics into a single cohesive simulation. Imagine a digital twin of our planet, a living, breathing model that is constantly updated with real-time data. This model won't just include weather and climate. It will incorporate urban systems, modeling how heat radiates from asphalt and buildings. It will include ecosystem dynamics, simulating how a change in rainfall affects a forest's risk of wildfire. It will model human activity, from traffic patterns to energy consumption. In this future, smart cities won't just receive a flood warning. They will automate their response. The quantum model, predicting a flash flood with street-level accuracy, will trigger the city's infrastructure, automatically close floodgates, reroute traffic away from low-lying areas, and send targeted evacuation alerts to specific buildings. It's a symphony of automated, intelligent resilience. Conservation efforts will be transformed. Ecologists will be able to use these models to anticipate how climate change will alter the habitats of endangered species. They could predict the shifting migration patterns of monarch butterflies and work with communities along the new route to plant milkweed, ensuring their survival. They could foresee where coral reefs are most at risk of bleaching and deploy resources to protect them. We gain the tools to become proactive custodians of our planet's biodiversity. This is the ultimate goal, a world where our technology is so deeply in tune with the natural world that it allows us to live not just on the Earth, but with it. Where there is transformative power, there is immense value. And the world is taking notice. Investment in quantum weather and climate modeling is no longer a niche scientific pursuit. It is a multi-billion-dollar strategic imperative for both corporations and nations. The economic and geopolitical landscape of the 21st century is being reshaped by this technology. The insurance industry, a business built on pricing risk, is at the forefront. For centuries, they relied on historical data to assess the risk of floods, fires, and storms. But in a rapidly changing climate, the past is no longer a reliable guide to the future. Quantum models offer a forward-looking crystal ball, allowing insurers to price risk with unprecedented accuracy. This will have profound consequences, incentivizing the construction of more resilient homes and infrastructure in safer locations. Governments are viewing this as a matter of national security and economic stability. When planning a multi-billion-dollar piece of infrastructure, a new airport, a high-speed rail line, or a sea-wall, you need to know it will be viable not just for the next 10 years, but for the next 100. Quantum climate projections provide that long-term certainty, guiding the development of resilient nations that can withstand the escalating volatility of our weather. This technology is becoming a new form of geopolitical leverage. The nations that master quantum climate modeling will hold a decisive advantage. They will be able to better protect their populations, secure their food and water supplies, and build more robust economies. They will understand the coming resource scarcities and climate-driven migrations before their rivals. In an age defined by climate uncertainty, the ability to accurately predict the future of the environment is one of the most powerful strategic assets a country can possess. We began our journey with the fear of an unpredictable sky. We've traveled from the chaos of a butterfly's wing to the incredible order of a quantum computer. We've seen how this revolutionary technology is already saving lives, transforming industries, and giving us the clearest picture we've ever had of our planet's future. The story of quantum weather prediction is more than a tale of technological achievement. It's a story about humanity's enduring quest to understand the world around us and to use that knowledge to build a safer, more resilient future. The ultimate lesson here isn't just that we have a powerful new tool. It's a reminder that our greatest strength lies in our ability to face monumental challenges with ingenuity and foresight. While we may not have a quantum computer in our living rooms, we can all adopt a quantum mindset. We can prepare for the future, not just react to the present. We can make choices in our homes, in our communities, in our policies that are informed by the best available knowledge and a long-term perspective. We can choose to be architects of a more resilient world. So I leave you with a couple of questions to think about. How would your own life or your community change if you had a perfectly accurate 2-week weather forecast? And beyond disasters, what industry do you believe will be most profoundly transformed by this new era of prediction? Thank you for joining us on this incredible journey. As we continue to explore the frontiers of science, I wish you all good health and a future filled with clarity and hope. And if you found this exploration as fascinating as I did, be sure to subscribe to our channel and hit that notification bell, because our next episode will take this quantum leap even further as we explore how these same breakthroughs are set to revolutionize space exploration, predicting solar flares, navigating asteroid fields, and perhaps even guiding humanity's first steps onto Mars. The future is closer than you think.